So right now we are on the convergence test. Before I start the convergence test, let me remind you about the integral test again, because last time we didn't do enough example here. So I'd like to do a quick review on integral test. All right, and I'll show you one example here. Show that this one converges or diverges. Okay, test this one for convergence or divergence. All right. To apply the integral test here, we're going to try to write down the associated function here. Ln x over x. And x here starts from 2. I do not start from 1 because ln 1 is just 0. So I start from 2. We have a few things that we need to verify. Is this one continuous? Can I plug in all the x value? Well, here I cannot plug in 0, but that's okay because k starts from 2. So it's kind of trivial. This guy will be continuous. It is also trivial that this one is positive for x greater or equal to 2. Positive because ln x is always, because ln x is positive for any x bigger than 1, okay? So that's trivial. Decreasing, however, is less trivial. Ln x increases, so the combination is less trivial. So to show f of x decreases, so these are the 3 conditions before I can even apply integral test. All right, to show this guy decreases, we calculate its derivative and show it's negative. I'm going to use the quotient rule here. So that's the quotient rule. So this will be negative when x is greater than natural number e. When you plug in e here, 2.7 something, this one will be 1. Okay, any number bigger than e will make ln 1 bigger than 1, and the sign of this fraction will be negative. So yes, it'll be decreasing. Okay, it will be decreasing. Thus, we can apply integral test. To actually imply integral test, I have to integrate this one from, well, the original series from 2 to infinity. So I will integrate from 2 to infinity. The function is ln x over x. We're going to integrate this. So this is an improper integral. So this is an improper integral. Sorry, obviously I wrote something wrong. That's not going to be infinity on the top. That'll be replaced with finite number t. And then we take t goes to infinity. So to evaluate this proper integral, you have to use a quick substitution. And I leave you guys to think about this, okay? So this is not that trivial, but I leave this for you guys to figure it out. When you integrate this, turns out antiderivative is ln x squared over 2. Okay, you plug in 2 and plug in t. So plug in t, plug in 2. So obviously when t goes to infinity, this one goes to what? Infinity, isn't it? And that's why the limit is infinity. Thus, the series diverges, okay? Series diverges. So that was a quick review on integral test. So let's continue with the comparison test. Sorry, I noticed the title is wrong. It's not convergence test. It's comparison test. Comparison test. Comparison test. For those who were at the lecture, I gave you one example like this. If you look at the notes that you wrote, and we have this direct comparison test that somehow just does not work here. Does not work. I mean, you can try it out. Many of you can notice that this original one is greater than this guy. So this one is bigger. And this is the p series with p equal to 3 halves. So I know this one converges. But the problem is the smaller one, okay, this is the smaller one, the smaller one is a finite number, does not say anything about the bigger one. That's why we say direct comparison test does not work. So there is nothing coming out of this, okay, there's no conclusion that you can get out of this. Direct comparison does not work. Direct comparison, by the way, is something we talked about before you took your midterm number 2. So today I will show you a new method, which is also part of comparison, and this time we call this limit comparison test. So that'll be pretty much your fourth test, okay? Fourth test. You have test of divergence. I need you guys to review all of this, okay? You have integral test that we talked about, we just reviewed. You have direct comparison test. So direct comparison test. That requires you to work very well with the inequalities and sometimes just very tricky. So here's the fourth test, which is called the limit comparison test. So you try to compute the limit of the ratio between two different sequences. If this is finite number c, so in other words, in the long run, a sub n and b sub n, they are almost the same. They differ by a scalar. For example, if a sub n is 1, then b sub n will eventually become very close to, say, c times by 1. Limit comparison test says if that's the case, then those two series behave the same. That means they either both converge or both diverge. So this is a very a strong result. It's very easy to work with. Because I don't need to play with the inequalities. I just need to calculate the limit. It is also easy to work with. It's also simpler than the direct comparison test. direct comparison. So let me show you how it works. So the example is the one that we cannot figure out use direct comparison test, which was the one we wrote a little while ago. This problem right here. Direct comparison does not work here, okay? I want you to go back and see why it doesn't work for those who just didn't see it. Here's how I can solve it. Use the limit comparison test. There's a limit here. There's this sequence that I have. Try to come up with something to compare on the denominator. So here we choose something that's very similar to this. That's actually always the case. Choose something very similar to the original one. The only thing that I've ignored is this minus 0.5. And try to find out the limit of this when n goes to infinity. Well, to rigorously calculate this limit, I divide the top and the bottom by n to the power 3 halves. I get a 1 on the top. I get another 1 here, followed by 0.5 over n to the power 3 halves. As we all know, constant 1 stays, constant 1 stays. And the limit of this is just 0. So that's how I know the limit of this ratio is 1. Limit comparison test says as long as this is a positive number, okay, that's not 0 because it's not going to work if it's 0. As long as it's a positive number, I don't care whether C is 1 or 2 or 3 or 1/2, that doesn't matter. As long as it's a final number like what we saw here, they will behave the same. And what do we know about this? This guy converges. The reason is because it's a p-series. And the p here is 3 halves. Okay, that's bigger than 1. And thus you can say by limit comparison test. Converges. Okay, converges. So that's limit comparison test. Here's another example. Solution. So once again, to do the limit comparison test, to find someone to compare with, you always start with the guy that you already have, and try to ignore the smaller terms and come up with something that you can compare with. So here I do the limit. It's always a limit, right, between the ratio of a ratio between the original series with someone that you want to compare with. That's the guy I'm going to choose to work with. Flip this around. I hope you can identify, or by divide the top and the bottom by 2 to the n, divide by 2 to the n, divide by 2 to the n. This one, okay, this one, I need you to think about why this one goes to 0, okay, 1/2 to the power of n, this guy goes to 0. That was one of the results that I asked everybody to memorize. R to the power of n always goes to 0 if R absolute value is between 1. Alright? So the limit of this 1 over 1 minus 0, in other words, 1. So it's a finite number that's not 0. And what do we know about this series? What kind of series this is? Some of you can spot what kind of series this is. For those who can't, plug in a equal to 1, a equal to 2, a equal to 3. So I can say this guy converges. because it's a geometric series. Geometric series is not enough for say this guy converges. It converges because it's geometric series with a special r, with r being 1/2. Okay, and it's between negative and 1. That's why it converges. And thus, by limit comparison test, the original converges. Converges as well. Okay. Sometimes you really have to be smart about the right series to come up with, to compare with, to do the limit comparison test. Take this guy for example. What are we going to compare this guy with? That's obviously the most important thing. Once again, you will try to leave behind the smaller terms. In this case, you're going to try to ignore negative 1. So you're looking at 1 over. You're going to leave this one alone. Okay, sorry, this n alone, followed by square root of n squared. All right, that gives you another n. So that's the guy you want to compare with. But make sure you calculate the limit correctly. Since this is a sub n, that's b sub n. Let's find out the limit at infinity. This becomes multiplied with n squared. Okay, multiplied with n squared. So it's n squared minus 1. So now what I'm going to do next is I'm going to divide the top and the bottom by n. I get a 1 here. N squared minus 1 over n. 1. And that's the same as square root of n squared minus 1 over, well, n squared. And the limit of this is 1. Okay, the limit of this is 1. This guy down here, this one underneath the radical is 1 minus 1 over n squared. It just goes to 1. Okay, that's why I say the limit of this is 1. All right, and thus they will behave the same. And what do we know about 1 over n squared? This converges because the p-series again with p equal to 2. See how often this p-series and geometric series comes into place here? Thus you have our conclusion. Okay, thus the original one also converges. Okay, also converges. All right. Here's one last example, and that looks somewhat tricky. You're wondering what's going to happen to this. And if you look at this guy, obviously it's tricky to come up with something to do the direct comparison test. It's just not a good idea. To do the limit comparison test, you have to come up with something to compare with. And you have to ask yourself what happened when n is large. Well, when n is large, I guess both n here will be a large number, 4 to the power of n and 6 to the power of n, they're all going to be large. But we can all easily tell that 4 to the power of n and 6 to the power of n, these are power functions that will be much, much larger than n, okay? So once again, we try to work with the larger terms, try to ignore the smaller terms. In this case, that happens to be the two ends. Okay, that happens to be the two ends. That's the original one, and I will try to compare with 40dn over 60dn. So you go ahead and figure out this limit. Use the fact that 40dn will be a lot bigger than n, and 60dn will be a lot bigger than n. And hopefully you can figure out the limit will be 1, okay? The limit will be 1. And this guy, we know, this guy is a, what kind of series? Think about that one, okay? This one converges because it's a geometric series. Write this apart and see what you see, okay? See what you're looking at. The ratio R is 4 over 6. In other words, 2/3. Now, once again, it's between -1 and 1. That's how I know this guy converge. And thus, once again, the original one converges as well. All right, and that's the limit comparison test, okay? And take some practice. So I will write down a couple problems, and you guys try to practice on the following few questions. Limit comparison, okay? So that's one more test. All right, it's practice time. I want you guys to think about what series to compare this guy with. It is true that many of them will be compared to geometric series. Some of them will be the P series. Okay, and please try all of these problems out. I can tell you the answer. All right, this one diverges. This one converges. This one also converges. Okay, and so that's the end of limit comparison test. And our next lecture will be 11.5, which is alternating series. That's the end of this segment.